Okay, welcome to linear algebra class. In today's class, we are going to talk about the material from part 3. So applied linear so part 3, we are studying low rank and compressed sensing. So what are the key parameters or key concepts in this chapter? The first chapter that we want to look at is what happens if you have some changes to equation ax is equal to b. So this is the equation that we have been trying to solve all the time. So we want to solve the equation ax is equal to b, and say we have solved this equation, but then this A matrix changes. Now what happens to the solution? Clearly the solution is going to change. But then does that mean we have to recalculate the solution, or we can use the previous solution and maybe update it a bit? So a classic example is, think about that you have a rectangular matrix and you have a vector, so x, and you have this known b. Please note this is m times n. And then what happens is you get a new data set, or you get something that increases the size of this, maybe by adds one more row. So it adds m plus 1 times n. So you get this row added. And with this addition of row, your x vector is now going to become m plus 1 rows time 1 column. So how do we find out this updated solution when this matrix gets updated? The second problem is you have this matrix ax is equal to b, but a has decaying singular values. And this problem may not seem apparent, but here is what happens. That what happens is you have sigma 1, then gradually you get sigma 2, then you get sigma 3, and sometimes these values, they decay exponentially. What it means by that is this sigma 2 is very, very small compared to sigma 1. Sigma 3 is very, very, very small compared to sigma 2. And when something like this happens, it is not possible to use the usual algorithms that we use for numerical computation to solve the set of equation ax is equal to b. The last part, and then we talked about what happens in this equation ax is equal to b A has multiple zeros. So in other words, your A matrix is sparse. And we looked at this case as part of compressed sensing in last class. But in today's class, we are going to talk about what happens when the matrix A changes and what happens when the singular values get decayed. So to set the stage, let me show you a very practical problem where this appears. So everyone knows about GPS. So in GPS, what you have is you have different satellites. So you have a satellite, you have another satellite, and you have one more satellite, and you have a GPS receiver on the Earth, and you have one more satellite. So you have a satellite 1, you have satellite 2, you have satellite 3, and you have satellite 4. And what you want to find out is you want to find out Y location and time. So the data which from satellites, you can find out these variables X location, Y location, Z location, and time location with the help of Earth center, Earth fixed coordinate frame, ECEF, which is from the center of Earth. And clearly this information can be used to find the latitude and longitude. But please understand the GPS satellites, the information or the data that is coming from these GPS satellites is noisy. So what happens is you may not be able to find out X, Y, Z, and T very accurately just from 4 satellite measurements. So what happens is you can have, say, additional satellites. So, and once you have additional satellites, clearly the accuracy of the solution is going to increase. But now this exactly is the problem that we have been trying to solve. So you have AX is equal to B. Your X vector is nothing but position X. I'm going to call this PX, PY, PZ, and T. This is what you want to find out. But the bare minimum number of satellites that you need to find these 4 unknowns is 4. But see, there are many satellites. So as more and more information becomes available or more and more satellites are visible to the receiver, we are going to get additional piece of information. So which means, please note, this A and this B will change. Now, in other words, the previous solution that we have computed may no longer be the valid solution, or it may not be the accurate solution that we want to obtain. So this is a very classic problem. How do we solve this type of a problem? So let me start with the initial setup. So the initial setup is something like this. Consider that I have a matrix A, and this matrix A is multiplied by a vector X, and B is the result. So at this point, for the sake of discussion, let's assume that A is given to us, B is given to us, and we are trying to find X. Now clearly, if A is a square matrix, so if this is n by n matrix, I can say X is equal to A inverse B. Now, here is a problem that is quite common. A gets appended. So say A changes its dimension in the next iteration by you have the original A, and this A gets added one row and one column. And I want to be very clear here. So this A gets appended by n plus 1 multiplied by n plus 1. And clearly your X will also get appended. You will have one more term here, and your B will also get appended. So now I need to find out this new augmented vector. I need to find out this new augmented vector. And some of you may say, hey, why not to do inverse? But now I want you to understand, consider the case that your n is say, and now your A becomes 100,001. Now the idea is, can I use this previous solution that I computed? Can I use? So the question is, can I use this A inverse that I computed, that was computed, to find inverse, of this new A? So that is the key question. So what has happened with the new addition of information, that A matrix got changed, and that A matrix that got changed is similar to the previous matrix, except there is one additional row and one additional column. And that problem is actually defined in terms of a very interesting problem called as Sherman-Morrison-Woodbury formula. So new A is perturbation, and perturbation means small change of initial A old. So how can I find out this perturbation? So let me write this perturbation. So the problem now is, I have A old, I have A inverse old, but now I got A new. I got this A new. I do not have A new inverse. So I have this is known. This is the new matrix, and I need to find this A new. So how is this problem set up? So what I'm going to do is, I'm going to write this problem something like this. So A new is expressed as A old minus a column and a row vector. So U V transpose. So A new is nothing but A old, and this could be plus or minus, it doesn't matter. But in terms of formula or in terms of equation, usually it is said as minus. So what this means is, I want you to understand, you have this A matrix, and this guy is basically, additional row and additional column. So that's what happened. So now you have a new matrix. So basically new matrix. This is your new matrix is nothing but your A old is A new, and you got this additional terms because of some changes. So the problem that I want to pose is, given A old inverse, can we find A new inverse? And please note, these values are known. And okay, the motivation is you have the GPS signal. Right now, the GPS signal is obtained from 4 satellites. Then the 5th satellite GPS signal gets available, and all of a sudden your A matrix becomes big, and now you want to find out the answer. And the answer to this problem is given by something called as, this is a very important result in linear algebra, which is called as Sherman-Morrison-Woodbury formula. Sherman-Morrison-Woodbury equation. And this equation is written something like this: a new inverse is equal to A inverse, and please note, A inverse is known. This guy is known. We found out from our previous iteration, plus A inverse U I minus V transpose A inverse U V transpose A inverse. Now, some of you may say, oh, this formula looks more complicated than the simple inversion. But please try to understand. And I want you to think about in terms of scale. So the matrix multiplication on the right hand side, this matrix multiplication is much easier than inverting A new. And that is the advantage of this formula. Like if you have this equation, what you can do is this equation can be computed very quickly on the numerical solution or numerical solver, rather than inverting the complete new matrix. Now, let me give you one more motivating example. Now, the motivating example is, say you have the classic least square problem. So what you have is, you have the data set and you want to fit a least square line. So you want to fit a line that is sort of the least square. And at this point, even though I have just shown 5 points, imagine that you have 100,000 points. You have 100,000 points. And all of a sudden, few new points get added. So all of a sudden, plus 10 points get added. And these points are these new points. Now, what you need to do is, based on, so UV is a vector. U is a vector and V is also a vector. So you can think about it, 1, 2, 3, is 4, 5, 6. So something like this. So U and V are vectors. So imagine that you are trying to solve the least square problem, and somehow you already have solved the least square problem and found the straight line that fits into 100,000 points. And all of a sudden you get additional 10 points, and clearly those 10 points are important, and somehow you need to include those in computing the new least square. And depending upon where those 10 points are, depending upon where this new data set is, your equation of line would change. Now in that case, what you want to do is you want to perform something called as recursive least square. So you already have a least square solution, but now you want to compute this new least square solution. So let's try to understand how this problem gets solved. So let's start with the problem that we are trying to solve. Is clearly our A matrix. In this case, since we are trying to solve a least square problem, is a rectangular matrix M times N. You have X and you have B. And what you want to do is you got this new information, with this new information, clearly your A matrix now becomes A time, and you get another matrix R, but the X will remain as is. And now you are going to have B, and B plus maybe M plus 10. So now you got, this was your initial system. And then what you did is maybe you did A transpose A X is equal to A transpose B. Then you did X is equal to inverse of A transpose A multiplied by A transpose B. And finally, you solve this equation, and now you are happy. This is what you got. But then all of a sudden, your system gets changed to this guy. Now what? So again, what you want to do is you want to start with the same process. What we did here is I'm going to have A transpose R transpose. I'm going to have A, I'm going to have R, again X, and then I will multiply this on the right hand side by A transpose, R transpose, and then I'm going to have this B and B M plus 10. The next step is obviously repeat what we did over here. But then at this point, I want you to understand that with a lot of computational effort, we already found out this value. So A transpose A inverse is already known. But to solve this system, to follow the process, what I need to do is I will still have to solve this problem, something like I need to do, so first row, first column. So let me write this down. So this will become A transpose A, R transpose R, X is equal to, I'm gonna get A transpose B, R transpose B, M plus 10. And the problem here, just like what I did in the previous case, is to find X, I need to invert A transpose A, R transpose R inverse, and multiply that by A transpose B and R transpose B, which is M plus 10. Everyone understood the setup? So the setup again, just for clarity, let me quickly explain. Initially, we are trying to solve a least square problem, and our least square problem has 100,000 points. And the only variable that we need to find out are say 5. Clearly, it's an overdetermined system. So we will actually set up the problem and then follow the procedures that is shown over here and try to find out the values of x's that are the most optimal in terms of L2 norm. And assume that in that process, we use the computational tools and we were able to find out the inverse of A transpose A. Note A transpose A is a square matrix. Then we got these additional measurements, and based on these additional measurements, now clearly the value of X needs to get updated. So what we did, we added those measurements, and now we got this appended system. So this additional equations that are shown over here, we obtained these additional equations. And now again, we want to repeat the same process, is find the least square solution. And when we set up the least square solution, I land up with this matrix, which is a perturbed matrix, which is different than the old matrix. So please note, this matrix is different than the previous matrix. And the trick here is, can I quickly use some numerical solution to find out the value of new A? And in that case, please note, this matrix is the perturbation of A transpose A. So given A transpose A, given the inverse of A transpose A, can I find out the inverse of the perturbed matrix? And for that, applying the formula, applying the equation, which is called as the Sherman-Morrison-Woodbury equation, this makes our life super simple. So the problem is A transpose A plus R transpose R, and I want to find out the inverse of this quantity using the Sherman-Morrison-Woodbury formula. This inverse can be written as A transpose A inverse minus C A transpose A inverse R transpose R A transpose A, where C is just a number. Please understand, C is just a number that is given as 1 plus R A transpose A inverse R transpose. So what this means, and this C value can be computed very quickly. And why can we calculate this value? Because please note, from our previous iteration, value of A transpose A inverse is known. Value of A transpose A inverse is known. R transpose R is not a big matrix, which is 10 by 10. So you can just multiply. Matrix multiplications are easy, inverses are super difficult. This guy is known and this guy is known. So you can clearly find out the values of inverse. Now, can I take an example and then explain how would this work? So let me take a very simple example. Say my A matrix is identity. My A matrix is identity, and my R transpose R is a matrix with all ones. So 1, 1, 1. So my A matrix is identity, and I know inverse of A is inverse of identity matrix is identity matrix. But what I want to do is I want to find out A minus R transpose R inverse. And some of you may say it looks simple, but it's actually not. Because if you look at the A matrix, you have an identity matrix. So this is 1, 0, 0, 0, 1, 0, 0, 0, 1. And you are subtracting this fully populated matrix, which is 1, 1, 1, 1, 1, 1, 1, 1, 1. So your equation, so final matrix is going to look like 0, minus 1, minus minus 1, 0, minus 1, minus 1, minus 1, 0. Now this matrix, as you can see, is not easier to invert. So you cannot invert this matrix just by looking at it. And you will have to perform some sort of computation. However, it is interesting to observe that in this particular problem, your R is nothing but 1, 1, 1. So I can use this formula and I can clearly find out the solution of A R transpose R inverse, and this is given at my just a simple expression. This expression, once you put in the value of A as identity, so and once you substitute the value of R, then you will notice that this inverse is given as I minus 1/2 1, 1, 1, 1, 1, 1, 1, 1, 1. So please understand that we don't have to do any numerical computation or inversions just by partitioning the matrix in form of A minus R transpose R and finding out the value of C. I can directly find out this value of the inverse of the matrix, and that can be quickly found out. So everyone understood the argument here. By using this equation, you can find out the inverse of the perturbation or the perturbed matrices very, very quickly. And this is going to be a workhorse when you are going to solve the data science or machine learning problems, because you will have to recursively solve this problem as the new information becomes available. So before I go any further, everyone understood the setup here, that I have solved the previous equation. Now, instead of resolving the previous equation with this new matrices, I'm going to correct the previous solution. Everyone understood this argument? So this is very much used in something called as recursive least square. And that leads to something called as dynamic least square. What is this dynamic least square? Now, least square is classically used on the static data. So what does that mean is when you have the data that is static, then you find the least square. Let me give an example of dynamic least square. The same problem. Now what you have is at time t is equal to 0, you have this data set. At time t is equal to 0, you have the data set. And what you did, you used your linear algebra tools and then found out that this is the straight line. Now, what happened at time t is equal to 0.1 second, that data changed. So you got that data got shifted. So this data got shifted. Now, clearly, the previous least square solution, which was valid, is no longer valid. So what you want to do is you want to update this least square solution for the new data. So, and this data is not static. So as time goes on, these points, they keep on changing. And using this new data, every time you will have to update your least square solution. And the classic example is the GPS tracking problem. Right now, the receiver is stationary, but the satellites are not. So which means the X, Y, Z, and T positions that you calculated when the satellites were in the initial configuration, what's going to happen is these satellites are going to move. In other words, the data that you are going to get at the receiver is going to change, which means even though your X, Y, Z, and T position has not changed because you were stationary, your input data has changed. So which means you would want to calculate the new X, Y, Z, and T position based on the new information that you received from the satellites. And assuming your calculations are correct, your new update and the old update, they have to be the same because you are not moving. So this is a simple problem. But now imagine that this receiver starts moving. So what is going to happen is the new information that going to come at you will be used to find out the X new, Y new, Z new, and T new. So your values are going to change. So what you want to do is you want not only the recursive least square, but you also need the dynamic least square. Now, however, please understand that you know at what velocity you are moving. So say for the sake of discussion, the velocity is known. So velocity is known. So you have some approximate information on the position. So you are going to say my new position, X new, Y new, and Z new is nothing but the velocity in the X direction multiplied by delta T, velocity in Y direction multiplied by delta T, and velocity in Z direction multiplied by delta T. But one thing that these velocities, will not be super duper accurate, or you may not have accurate measurement of time. So essentially what you have is, you have some sort of model that gives you some prediction of future. So it gives you some estimate of future, but you want to correct this estimate based on the new data that you are receiving. And this problem is an ideal setup for something called as the Kalman filter. So Kalman filter. So what is a Kalman filter? Kalman filter is nothing but a algorithm for dynamic least square update. So Kalman filter is the combination of the update or recursive least square and the dynamically changing data. So let me write this down in terms of what we learned so far. So you have A, then you have X old, and then you want to find out X new. So you have, and then you have some additional information which gives you the difference between the previous position and the new position, that I will just write this down. So you have this setup is equal to value of B is known. You know your velocities multiplied by delta T, that gives you incremental distance, and you have this additional information. So let me set up this problem. This is the old data from GPS. This is the new data or additional data, GPS data. This is the old solution that we computed. So this is computed. And this is the new solution to be computed. And this R value is update or the measurement update. So this is measurement update. So the Kalman filter problem is something like this. Given the new measurement, how can we find out the new solution? And there is additional stuff that goes inside it, because depending upon how the measurement is changing, depending upon the variances and covariances, depending upon the noise in the data, you can actually come up with a fairly accurate representation. So what you do is your new solution. So new solution, and this is super important, new solution is given as your old solution plus some type of a gain, your new update or new additional data minus R times your state estimation. So this is estimated. This is known. And this is called as the Kalman gain. This is the new additional data. This is called as the Kalman gain. So this is a workhorse in guidance system, missile guidance system, or the aircraft guidance system. Kalman filter is used again and again in lots and lots of applications. for data smoothing. Kalman filter is used for sensor fusion. The data coming from multiple sensors that is combined, and the optimal solution is obtained. So please understand that the technique that we talked about is very clearly applicable for signal processing, machine learning, GPS, inertial navigation, and tracking. So again, we will have a separate discussion on Kalman filter, but I want to make that connection at this point, that Kalman filter is dependent on recursive least square uh, approach that we talked about and the formula that we discussed. Any questions on the material that is discussed so far? And this is theory part, so perhaps it's difficult to appreciate, but all these concepts are super useful when we actually solve the MATLAB problems. Now let me make this problem a little bit even more complicated. So we said A old is transitioning to A new. But now A new and A old, this transition is time dependent. So this is time dependent. What does that mean? In other words, your matrix A is now function of time. So if the measurements are noisy, that is a very good question. The measurements are noisy, then you look at the type of noise. So you look at the covariance. Yes. So you look at how, if those measurements, so I did not mention here, but there is a concept which is called as covariance. So you have the measurement covariance, and then you have the system or the noise. So what you do is you actually see, and let me give you what that means. That means the new measurements that are coming in, do they have some sort of mathematical relationship, some statistical relationship with the old measurements? So that gives you covariance, means how they vary together. So that gives you covariance. And sensor noise, which means how noisy the sensor is. So for example, even though we expect the sensor data coming to be super clean, but unfortunately the sensor data is going to be noisy. So how do we use these noise parameters and then still be able to get the accurate solution? So this estimated solution is computed based on the noise and covariances. And just to, yes, you can use covariance to measure the noise. That is correct. Same technique, the Kalman filter is used in Neo 6M. Believe it or not, Kalman filtering is used in Google Maps on your iPhone or your Android phone to pinpoint your location. So if you use your phone in the background, the Kalman filtering is working. Now, sometimes you have noticed that if you are using your phone and you are using Google Maps and you are walking from point A to point B, your position gets updated. So what is happening? Your phone has 3-axis accelerometer and 3-axis gyroscope. So by integrating accelerations 2 times, the phone or the software can compute approximately the new position, the difference between the new position and the old position. So basically, your phone is giving you this V multiplied by delta T. And the GPS receiver in the phone is going to give you this new data set, and the software excuse me, software in the phone is going to calculate x new based on the GPS update and the position update. So that is the crux of Kalman filtering. So believe it or not, your phone is performing Kalman filtering in the background to, and then finally as your position gets updated, you will see that dot on the Google Maps moves ahead. And then again it looks at the the map features. So even if your solution is outside the road, it will have some constraint and you get placed on the road. So that is how the navigation and tracking works. So to answer the question, yes, Neo 6M would use Kalman filtering to find out the update. So all GPS receivers that you are familiar with or you have used, they used Kalman filter. Any other question? So now this is the key question, that the new measurement or new matrix is now dependent on the time. So your matrix is time variant. So what happens now? So in this case, we can use the concepts of something called as time varying eigenvalues. We can use time varying eigenvalues, and we can use time varying eigenvectors to find out the reasonable solutions. And this is sort of a little bit new to understand, because usually we are not familiar with time varying eigenvalues and time varying eigenvectors. So you have lambda t, which are eigenvalues. Bear with me for a second. For some reason, my Apple Pencil is not working. Let me try again. So eigen values, and you have a concept of time varying eigenvectors. So eigenvectors. So concept of time varying eigenvalues. Yes, application in machine learning is a very classic example is the facial properties are changing. For example, if you want to perform a facial recognition and the person is walking, so or in other words, you are trying to find out the license plate detection. You want to find out your number plate, but the vehicle is moving. So every time the image that you are gonna get, that image will be a little bit displaced. So so based on these displaced images, how do you still able to recognize the accurate number plate? That is an application in machine learning. So Kalman filters are also used in machine learning, wherein the image data is continuously changing, or then identification when the person is moving, or identification when if an object is moving. So these are the typical applications in machine learning for Kalman filtering. Okay, so next thing is, if you have your A matrix that is time varying. Now, when the A matrix is time varying, we have to have the eigenvalues and eigenvectors that are time varying. If A matrix is square, if A matrix is square, then clearly okay. So if your A matrix is square, if your A matrix is square, then you are going to have lambda t and xt. So these are time varying eigenvalues, and you have eigenvectors. If your AT is rectangular, then you are going to have singular values and singular vector. And these will be dependent on time. So how is eigenvalue problem expressed when you have a time dependent A matrix? So the key question that I want to address here is how AT is related to lambda t and xt. So straight away, this is something that we want to understand. For time invariant matrix, AX is equal to lambda x, which means when A is a constant matrix. For time varying matrix, you will have AT xt is equal to lambda t xt. But in addition to this, there is one more equation that is super duper important. Whether you know this or not, please understand, if you have the transpose, so there is this equation that I want you to remember. So yt multiplied by a of t is equal to lambda t multiplied by yt transpose. So this is super duper important relationship that I want you to understand. And xt and yt, these are two time dependent vectors. They satisfy this relationship xt multiplied by, so y, so actually I wrote this incorrectly. This is yt xt is equal to I. This relationship is super duper important, and let me tell you what does that mean. So if you have a time varying eigenvector, for that time varying eigenvector, there is a complementary eigenvector which is given by y. So you have x of t that changes with time. For the time varying eigenvector, you have a complementary eigenvector that is given by y. And the relationship between the complementary eigenvector yt and xt is that yt transpose multiplied by xt is going to give you identity matrix. Yt transpose is multiplied by x of t is going to give you an identity matrix. So that is a very important relationship that I want you to remember, because that equation will be very useful when we work out some problems. So with this, that gives me the equation. How do we find out value of lambda t? To find the eigen values which are time varying, we find out this eigenvector which is time varying, multiply that by the A matrix, multiply that by this x time eigenvalue, and the derivative of the eigenvalue d lambda over dt is equal to yt multiplied by dA over dt multiplied by x of t. Now, something that I want you to understand, that this is important, that these equations we don't actually solve by hand. These equations are coded in some sort of MATLAB or Mathematica or some sort of a program that allows us to find out these eigenvalues and eigenvectors that are changing with respect to time. And when we take some examples, this concept will be very clear. Like what would be the classic application where something like this can be used. The other equation that I want you to follow, this is super important. So if you have a time varying A matrix, and if you have a time varying A inverse matrix, and if you multiply these two, so A inverse T, even though they are time varying, the product needs to become time invariant. So please note, A matrix is time varying, A inverse matrix is time varying, but even though the matrices are time varying or whether the matrices are time invariant, when they are multiplied together, their product is going to be an identity or a constant. So if I want to find out the derivative dAt by dt, I can use the chain rule, and that gives me this equation. And this equation is sometimes useful to find out. So just to give you an idea, so if I want to find out dA inverse by dt, I can find out that by AT inverse negative sign multiplied by DAT by dt multiplied by AT inverse. So this equation is used if you want to find out the time varying inverse of the time varying matrix. So derivative of A inverse is used in a lot of applications, especially, and this equation is given on, but I derived this differently, page 163 of textbook. So if you have time varying matrices, then we can use the time varying eigenvalues and time varying singular values to solve the problems. So in the same spirit, let me just go ahead and give you the derivative equation for singular values. So singular value problem, as you know, is A is m times n is equal to, you have U sigma V transpose, and the singular value problem. Now, if you have a time varying matrix, will be U that is dependent on time, sigma that is dependent on time, and V transpose that is dependent on time. So this is the time varying singular value problem, and derivative of singular value is given as d sigma by dt is given as u transpose t dA by dt v t. So this is the time varying singular value problem. So singular value problem, time varying. And the next part, which talks about the interlacing of eigenvalues and singular values, that we don't actually are going to we don't need to discuss, because that shows you how these values change, and those are applications of interlacing in information theory. So if you are going to take the courses in information theory, these concepts will be super duper important. So if you are from electrical engineering, if you take advanced classes in information theory, then you would use these concepts. The next part that we talked about is the application of compressed sensing. So if you look at the textbook, then the last section, which is section 3.5, is it talks about the compressed sensing. So section 3.5 talks about the compressed sensing, and in this section we talk about the different BCs, different sparse matrices, different norms. So we talked about the L1 norm, we talked about the L2 norm, we talked about the L infinity norm. We also talked about something called as the lasso, wherein if you look at, we solved the problem with lasso, which is combination of L2 norm plus L1 norm together. And then we actually looked at some penalty methods. The last problem that we worked out in the class, we looked at the penalty methods to find out the least square solution using L2 formula and L2 plus L1 formula and L1 formula. So if you use L1, that gives you sparse solution. If you use L2, that gives you least square solution. And sometimes we use L infinity to find the maximum difference between the 2 points, and then we use L infinity norm to find the solution. So in today's class, quick recap, we talked about the mathematical machinery that allows us to do the MATLAB computations that we did in the last class. Then if you were to look at the theory of different algorithms for sparse computation, L2 computation, that is given in the section 3.5, which talks about algorithm for matrix completion when your matrix is sparse, and then how to find out the different solution. But L1 norm allows us to find the optimization problems which are non-convex. So in other words, the problems that cannot be solved using traditional optimization techniques can have a solution if you use the L1 norm. So that is the advantage, and that prepares us to move on to the machine learning part of the section. So we will try to talk about a little bit of Fourier transform and different matrices that are important in linear algebra. And then what we would do is we would move on to the machine learning and data analysis using the linear algebra techniques. With this, I'm going to stop here, and I would be happy to answer any questions you may have.